Hey, it's ChemHive. Welcome to part 2 of our thermodynamics journey. In part 1, we covered the basics of thermodynamics. Now we'll dive deeper into the fundamental laws that govern energy, heat, and entropy, which are essential for understanding physical and chemical processes. This section will focus on energy transfer, work, and heat, and how these concepts are applied in real-world systems. Let's explore how energy flows and how we can harness it for efficiency and performance. Let's start with the zeroth law of thermodynamics, which states that if system A is in thermal equilibrium with B and B with C, then A is with C. This can also be described or defined as thermal equilibrium, which is a condition where two systems in contact no longer exchange heat. Equation: if TA equals TB and TB equals TC, then TA equals TC. This enables the definition of temperature as a measurable property. Next is the first law of thermodynamics, which states that energy cannot be created or destroyed, only transformed, and is defined as internal energy, U, is the total energy contained in a system due to microscopic motion and forces. Equation: delta U equals Q minus W, where delta U equals internal energy change, Q equals heat added, W equals work done by the system. The second law of thermodynamics states that entropy of an isolated system always increases, where entropy is a measure of the disorder or randomness in a system. Equation: delta S equals the integral of dq rev all over T. The second law of thermodynamics also tells us that heat cannot spontaneously flow from cold to hot, where delta S is the change in entropy. dq is the heat exchanged in a reversible process. T is the absolute temperature of the system. This explains why 100% energy conversion to work is impossible. The third law of thermodynamics states that as temperature approaches absolute zero, entropy approaches a minimum. Absolute zero, which is 0 Kelvin, is the point at which a perfect crystal has minimal entropy. Equation: limit, as T approaches 0, S equals 0, where S equals entropy of the system, T equals absolute temperature in Kelvin, explains why absolute zero can't be reached. Here are some applications of thermodynamic laws: design of heat engines and refrigerators, optimization of energy processes, understanding chemical equilibrium, and materials science and cryogenics. In this tutorial, we've reviewed the 4 laws of thermodynamics. In our next part, we'll review the following: thermodynamic properties, cycles, phase diagrams, and equilibria. Thanks for watching. Like, subscribe, or follow and turn on your notification so you don't miss the next part and other educative videos to come.